All right, let's start. Okay, so the exam is tomorrow night, 6:30 p.m. in the Hall of Music. Once again, make sure you find out where you're supposed to go. We're going to sit by TA, find out where your TA section is. Top of the chart is the front of the room, the stage. Okay? Like I said, I've been saying if you get lost, look for your TA, number one. If you can't find him or her, go to the stage and get my help. I know some of you have an exam at 8, so it is very important that we start our exam on time. That means you need to get there on time. If you get there at 6:30, we probably will start without you, okay? Get there early enough. A couple things before we start the review. If you've never seen a Scantron at Purdue, the Scantrons we use, they look like this. There will be two versions of this, a green one and an orange one. They should match the color of the cover page of your exam. So if you get a green exam, you should have a green Scantron. Do not do a green exam with an orange Scantron. The result is not going to be pretty. Okay? Now it's got basic stuff on here, your last name, first name. This thing, section number here, that's actually a quite important number. I sent this to you by email, but please do try to remember your section number. If not, we'll remind you at the exam tomorrow night what your section number is. The section number makes sure that your score goes to the right person. If you have the wrong section number or no section number, your score may get lost. We'll have to track it down, and that's not good. Right? It's not good for you. So make sure you have the right section number. So look for it. The table I got on the other projector here is also in the email I sent yesterday. And then the answers will be put here. There will be 12 questions, 5 choices each, and each one is worth 8 points. And if you do the math, 12 times 8 is 96. So you get 4 points for just showing up. And then ID number, of course. All right. Okay, don't count down those 4 points to save you, though. Okay, so we're going to do, oh, by the way, there's an SI session tonight. $5:30 p.m. in Weather Row 420. Is that right, Nick? Thank you. Okay, so we're gonna go through. I selected a few questions from past exams that are relevant to the exam you'll get tomorrow night. So we're gonna just cover some of these major topics. The first thing we'll review is domain. Remember, when we look for domain of a function, we look for 3 things we don't want to happen. We don't want to divide it by 0. We don't want any negative number under even root, square root, 4th root, 6th root, that kind of thing. And we also want to avoid the log of any negative number. All right, so here's a function from one of the past exams. I forgot which one. But you were supposed to find the domain of this function right here. And this one's got all 3 of these things included here. Okay, we'll check out one of these one at a time. So the obvious thing to start is the numerator here. And by the way, no log of negatives or 0, right? You cannot take the log of a 0. It has to be a strictly positive number. So the numerator with the natural log there, a natural log of x minus 2, we require x minus 2 to be strictly positive. Cannot be 0. So this means that just looking at the top alone, we need to have x is greater than 2. For the denominator, normally we can have 3 minus x equal to 0, but because it is in the denominator here, we also require this to be strictly positive. And because we're dividing by that, we can't allow a 0. Right? So this tells me that x 3 is greater than x, or x is less than 3. Now, any number that satisfies both of these conditions will be part of the domain. So any number bigger than 2, wait, hold on a second. That's right, any number bigger than 2, but less than 3, right, will be allowed. So therefore, anything bigger than 2, so we can write it as x is greater than 2, not including 2, but less than 3, not including 3. Or in the interval notation, which be sure you know how to go from one to the other, at least be able to recognize that they are the same thing. The answers may be given in this way or the interval notation. Make sure you know both. Okay, so domain question should be the one that everyone gets. Right? There's a very simple thing, 3 things to look for, and typically it's not very difficult to find out the domain. The next thing we'll look at is the graph transformation. And we'll do a review by using one of the old exam questions again. The question says the graph of y is equal to f of x is moved horizontally three units to the right. And then reflected across the x-axis. What is the resulting equation after the two transformations? I think this one is from fall 2014 or something like that. I don't remember, but it's one of the ones I grabbed from an old exam. We don't know what the equation looks like, but we know how to, in general, change these things. So graphically, what we got going on here, we don't know what f of x looks like. Let's say it looks like this. We're going to pick it up and move it to the right, 3 units. So this point right here is going to move over here. So after the first move, we get this. Okay, and what would the equation look like after that move? Y is equal to? Where does the minus 3 go? Very good, inside the parentheses, right. Right, you change x when you want to move right or left. If I want to move this thing up 3 units, what would this look like? Plus 3 on the outside, right? Good. All right, so then we're going to reflect this, the resulting thing, across the x-axis. So it's an up and down reflection. So next move is to reflect this guy down here. All right, so how would you do that? Negative in front of the f, right. So it's easy to remember. Whatever y you used to have, now you want it to have the opposite sign. That's what the reflection does. So whatever these were, move it down. If these were negative, the negative moves it back. So it's a reflection. Okay, so we get negative of f of x minus 3. Be sure you also look up the variations of these. If I move this up or down, reflect across the y-axis, that kind of thing. Compression and stretch. Make sure you look those things up. Okay, you'll see a transformation one. It's not terribly difficult, but just test your basic knowledge of the transformation. All right, so those are the things that should be easy stuff. You need to know how to find the inverse of a function. By the way, you should also know that the function can be inverted if what happens? Good. If function is 1-to-1, good. And how would you check for 1-to-1-ness of a function? Right. If you plug in a given x, do you find multiple y's? If you have a graph, what's a simple way to do it? Yeah, horizontal line test is a very easy thing to do. All right, so if you know something is 1-to-1, and then you have to find the inverse of such a function. So here's an example, again, an old exam question. If the exam question says, here's f, find the inverse, you can assume it is 1-to-1, right? Just go ahead, assume this is 1-to-1. Otherwise, we wouldn't ask you to find the inverse. If we want to test you this kind of thing, we'll have a question that tests if you know how to determine if something is 1-to-1. Be sure you know that, and of course, know how to find the inverse of a function. Okay, remember what we want to do here. If we replace f of x with a y, the first major thing to do is to find x, solve for x. Y as a function of x right now, we like to switch that around to find x as a function of y. That eventually, simply by a change of variables, gives you the inverse. Okay, we got two x's over here. Let's try to get them all on one side first, but not in the form of a fraction. The obvious thing to do here is to simply multiply across first. Distribute. Let's now subtract 3 to the x from the right to the left and subtract this 2y to the right. Now I got x's on one side, not in the form of a fraction, and then everything else on the other side. Let's get rid of the excess stuff. Factor 3 to the x divided by y pi minus 1 All right. So how do we get this x to come out of the exponent? Log base 3, do I have to use log base 3? Can I use natural log? Why not? What's wrong with natural log? If my goal is to get an x out of the exponent, right, but it still accomplishes my goal to get the x out of the exponent, right? So in principle, you can use any log, but you're right. Normally, we would use the log that would simplify things the most. So natural log, log base 3 would be a pretty good choice. However, remember, any log allows you to move the exponent around. So if all you want to do is to simply move that x out, any log is fine. But what do log base 3? That makes it the simplest. This gives me an x. Right-hand side is a log base 3 of all of this stuff. Okay, and that essentially is your inverse function. The last step is purely cosmetic. We'll call x the f inverse of x. We exchange x and y and then rename y to f inverse of x. Okay? By the way, remember we can also write this thing right here using properties of the log if you choose to. It all depends on the choices given to you, the 5 choices. Okay, so sometimes you may have to rearrange things a little bit if you don't find your answer as part of the 5 choices. For example, right here, you may have to do that just to make things fit. Questions? Good. Now let's do a little bit more review on logs and exponentials, stuff along that line. Oh, by the way, you saw my email that I extended the homework. That was the 2 that were due last night. They will be due tonight instead because there was some kind of, I guess, power was down yesterday. Anyway, if that affected you, don't worry. The homework is not due until the homework's due tonight at the same time. If that didn't affect you, well, good for you. Be sure you know the basic properties of logs and exponents. Here again are 2 questions from old exams. We have e to the 4 minus 2x is equal to 1 over e squared. I would like to find out what x is equal to. The very, very easy way to do this one right here is to rewrite it as e to the minus 2 on the right. Okay, and then for these things to be equal, they have the same base. The exponents have to be equal. There's no other choice. So this right away tells you 4 minus 2x is equal to negative 2. Therefore, 2x is equal to 6, or x is equal to 3. Or you could just simply take the log, like in the last example we did. Take the natural log on both sides. Natural log of e to the something is 4 minus 2x, is the same something. The right-hand side, you still want to write it as e to the minus 2. Natural log of e to the minus 2 is minus 2. So there, you get the same equation you have to solve in the end. 2x is 6, x is 3. All right, so that's simple. You don't always have to take logs. If you can get the two bases to match up somehow, then just make the exponents equal. Here's a log 1. Okay, with the log equations, remember, you have to be very careful with the domain. You may get a solution that's not in the domain of this function. So if you get a solution that's not in the domain, that must be rejected. So we'll come back to that after we solve this thing. For now, but got to keep that in mind. Okay, there's a bunch of different ways to solve this. One way to do that is to use the basic properties of log. Right? So we got this here, log of the top minus log of the bottom when you start with a fraction like that equal to 0. This is also equal to log of y plus 3 minus log of y minus 1. Oops, never mind. That's fine. Oh, forget that. I don't know what I was doing. Here's what I wanted to do. Equal to log of 2y minus 1. There we go. Okay, so you see, it's just like the exponential thing. It's the same log right here. And the only way this can be true is if these are equal. Y plus 3 is equal to 2 times y minus 1. And it becomes trivial from this point on. We have 5. I brought the 2 over. Now subtract the y here. Y is equal to 5. Okay, is y equal to 5 acceptable? What's the domain of this? Y cannot be 1. That's obvious, right? Y cannot be 1. And this entire thing has to be positive. Will this make the whole thing positive? Yeah, right? That's an 8, and downstairs is an 8. That looks good, so that should be fine. Okay, so that's the right answer. Sometimes you get two solutions, and you have to check both of them. If one doesn't work, you have to throw it out. If both don't work, you throw everything out. Then the conclusion is then that has no solution. A shorter way to do this same thing, a more direct way, I would say, not necessarily shorter. we know that log base any base of the number 1 is equal to 0. Log of any base of 1 is 0 automatically. So log base 10, implied 10, of this thing is equal to 0, meaning y plus 3 over 2 times y minus 1 must be equal to 0. And then from there, we solve the same way, right? Y is equal to 5. Okay? So these log equations, sometimes you can find a shortcut to do these very quickly. Not always, but sometimes. All right, and then a major topic, limits. So just make sure you go through all the different kinds of limit problems you've seen. Look at the homework. Make sure you know every single limit problem on your homework. That's for starters. Then do a bunch of more exercises from the old exams or the book problems to get even better if you feel that you need to. Okay, so here are just some miscellaneous old exam problems I found. We'll work through these. Limit as x approaches 1 from the right side of 1. X minus 4 over x squared over x plus 1. All right, so what do we get? What do you think? Negative 3 halves. Anything else? What's that? Negative 3 halves. Okay. Oh, I see the problem here. I meant this to be a minus 1. Okay. Now how does that change? Sorry. How does that change the limit? The other one was trivial. That was a waste of time. Sorry. How about this one? What do we get? I can't plug in minus 1 anymore, right? So my limits could be infinity, minus infinity, some number, probably not. Well, basically down to the two infinities. How do we decide? Look at this sign. Okay, so here's the way you can handle this kind of problem. When you want to approach minus 1 from the right side, you're looking for something that's just a little bit bigger than minus 1. For example, minus 0.9999, for example. Okay? That's a number just slightly bigger than minus 1, coming from the right side, something slightly bigger. Now, this goes into the numerator, would be a negative number, right? The denominator, x squared is always positive. That really doesn't change the story. This thing right here, x plus 1, this will give me a very, very tiny positive number. So you have a negative number that's around minus 5, nearly minus 5, over a tiny positive number, and the limit would be, what would you get as a limit then? Minus infinity, very good. Okay, about roughly minus 5, I'll write it down here. Minus 5 divided by tiny positive number is a big number, but retaining the negative sign. That's the way to handle this kind of thing. That's how you decide if this thing goes to positive or negative infinity. How about this one? X minus 3 over x squared minus x minus 6 as x goes to 3. Yeah, first of all, the thing you want to notice is that this goes to 0 over 0. 0 over 0 means if you can factor them, factor anything here, you want to do that. Factor and cancel with polynomials. If you cannot do that, if you have roots involved, if you have radicals all over the place, consider rationalization. Rationalization. So these are your possible next step. These are obviously polynomials. We'll look at the factor and canceling way. If these involve radicals, then I would rationalize them. You want to find out what's causing the 0 over 0. So factor the denominator here. All right, so we see what's causing the 0 over 0. It's these two x minus 3s. X goes to 3, but not equal to 3 means these are never 0, but we can cancel them. Okay, now when x goes to 3, this gets close to 5. So it's 1 over 5 as the limit. Okay, questions? All right, let's do another one. Limit going to infinity. These are usually pretty easy, especially all you got are polynomials. So you should be able to get this without doing anything. What's the limit? Oh no, I heard more than one thing. Okay, let's try again. What's the limit? 3 over 7. Good, much better. What would change if I remove the square from the top? This one here. 0, good. What about if I remove the square? Oh, I can't do that, can I? How about just 7x there? How about this? Infinity, good. Right? The numerator has bigger power, so that dominates the downstairs. Much bigger infinity over a somewhat big infinity is a big number. Okay, so when you got rational functions, these are very easy. Same powers, look for the coefficients. This one is the numerator with higher power. Limit goes to 0. No. Lower. This one is the numerator with the right. Now in that case here, you have to decide what the sign of that fraction is. If it's always negative, then it will go to negative infinity. Here, both of these are going to be positive when x goes to positive infinity. So the overall limit would be positive. Okay, so Rational functions are easy. It gets a little bit tricky when you have things like exponentials. Okay, so look at this one here. Limit x goes to infinity, e to the x plus x over x squared minus 2 e to the x. How would you do this one? Right, exactly, right? Exponential versus a linear. Exponential is going to dominate when x becomes large. When x is large, e to the x is much bigger than just a plain x. Think of e to the 1 millionth power. That's e times e times e times e, 1 million times, compared to the number 1 million. That is obviously much, much, much bigger. Same thing downstairs. So this means that e to the x plus x is roughly simply just an x, essentially. In the denominator, same kind of thing happens. This is still going to be much, much, much bigger than that. So that, when x is very large, is basically minus 2 e to the x. So the limit of that thing would be essentially this, right? And this would go to minus 1 over 2 as the limit. Okay, so it helps. You can also, what you can also do is to divide the top and bottom by e to the x, and then just go through the more lengthy way to do that. Or you can use reasoning here to cut a little bit of that work out. By the way, what does this number mean in terms of a graph? Right, horizontal asymptote. To the right, on the right, right? The right, because x is going to infinity, so we're looking at the horizontal asymptote on the right. What would the limit be of the same function if we're going to negative infinity? Same thing? Or what's the number? It's not the same thing. No. 0, I heard 0. So we're going to be doing that reasoning again. Remember, e to the x goes to 0 if x is a large negative number. Because e to a large number goes to infinity, e to the x to a negative number, e to the minus a million, is 1 over e to the million, which is essentially 0. So when x is going to negative infinity, this is some large negative number, but this guy is going to 0. This guy is going to 0. That's some large positive number. So this is going to be essentially the same as if the e's weren't even there in the first place. Okay, e to a large number goes to 0. And these two don't go to 0, they remain. And this has a lower power downstairs, so that would give me an overall limit of 0. Okay? Function like that would have the same horizontal asymptote to the right and to the left, on the right and on the left. But for e, and if you see anything involving radicals, then there's a good chance that the horizontal asymptote will be different on the two sides. that's the horizontal asymptote on the left. Questions? Okay. All right, next major topic, continuity. Remember the three things that have to happen for a function to be continuous at a specific number. First one, obviously, that function has to be defined. 2, the limit must exist. 3, whatever the function is equal to, must be equal to the limit at that location. Here's another problem from one of the old exams. The function h of x is defined as x squared minus 2x minus 3 over x plus 1. Whenever x is not equal to minus 1, it is defined as the number c. If x is equal to minus 1 exactly, we would like to find out the number c such that this function would be continuous at x is equal to minus 1. Oh, by the way, what type of discontinuity might this be? A whole, and what do we call that kind of? Removable. Good. What are the other types of discontinuities we have seen? Asymptote, jump, right. So we have a jump, asymptote. Those are not removable in any way, but an open circle, a hole like this one, would be removable. Okay. All right. So let's see. H of minus 1, of course, is c by definition. So condition 1 is true. Now let's check the limit. We want x to approach minus 1. That means we want x to be not equal to minus 1. So we don't look at that. That's only true when x is exactly equal to minus 1. When we go to minus 1, we don't want to be at minus 1. So we look at that one here. This is very much like one of the ones we saw earlier. You get a 0 over 0, which means you can factor and cancel. So we get minus 4. Okay? The limit is approaching minus 4. The value of the function is defined as c. So conditions 1 and 2 are met. Number 3 means that c must be equal to minus 4. Now if we make c equal to minus 4, then this function would be continuous. Okay, so we remove the discontinuity that's on this function here by defining C, a point at this number here exactly. Make sure you know the definition of a derivative. Remember, things like the product rule and quotient rule and power rule, that stuff will not be on the exam. But for the exam, be sure you know the limit definition of a derivative. Okay, look at the homework questions covering this kind of thing. On the homework you had just basic simple functions given to you, and you had to use the definition to find the derivative. Make sure you know how to do stuff like that. Be sure you know that the derivative can mean several different things. The most basic thing it could be is the slope of the tangent line. It can also represent the instantaneous rate of change. Make sure you know how to do the homework problem of the type where you're given the graph of something with or without the equation. Make sure you know how to find the graph of f prime from that. And actually, I have an old exam problem on that, so let's take a look at it. Okay, so here we have the graph of f, whatever it's equal to. Whatever the equation looks like, not a big deal. What would the tangent line slope at these locations be? Doesn't exist. The graph is not, the function is not differentiable. Whenever you have a cusp, a corner, or a discontinuity, the function is not differentiable. And that's why the graph of f prime should not be defined at those locations. Okay? So at 0 and 2, the graph of f prime should not be defined at all. This one has a f prime defined here, so that cannot be it. Neither can that one. So these are out. So you're down to here, here, and here. Okay? So then we see that here it has a constant slope. Slope never changes. So that means there will be a constant value on the two ends. This one has a slope of positive number, so one of these looks right. That has a negative slope. So looks like we're looking at A, right? Do we agree? A. Because this guy here has 0 slope. F prime of x is equal to 0. So there, that's the only one that fits the description. All right, that's it. See you tomorrow night.